Start. So, Vikram, are you ready?
I am about 10 seconds away from being ready. Sorry, I had to quit and
No problem.
Start in order to share my screen.
Perfect.
I'm ready.
Yes. Okay, so the first speaker of the session is invited speaker, Vikram Ravi, who's going to tell us about DSA. Let's welcome Vikram.
And thank you so much for having me here to speak as well. Can I just confirm that you can see my slides okay?
Yes.
I'm sorry, I think that literally as I was saying that, something happened. Can I just confirm that you can see my slides okay and hear me okay?
Yes.
Great. Let's get started then. So, I will be telling you today about various aspects of FRB science with the Deep Synoptic Array program, which is really a conglomeration of instrument development projects here at Caltech, not all of which are focused on FRBs, but certainly some of them have been initiated with the goals of detecting, discovering, and localizing FRBs to specific sources. So the Deep Synoptic Array, the DSA program, was initiated by Greg Hallinan and Sandy Weinreb in 2013, but then really in 2017 we realized that by just building an array of 10 antennas, these are 4.5 meter dishes, we could really have a good chance of detecting and localizing an FRB, something at the time was quite a novel case. This led to the STARE2 project, where we took a few of our feeds and pointed them up at the sky in order to be a very insensitive but very wide field FRB detector. This was work by my student Chris Bohanec. The success of both DSA 10 and STARE2 led to the DSA 110 array, which is now discovering and localizing FRBs. And we're hoping that in the future, these projects will lead to two new directions. One being the DSA 2000, which I'll say a little bit about, and the other being a concept which I haven't really talked about before to an FRB audience, or indeed any audience, being the track instrument, the transient radio camera. So, in short, we build instruments in this program, and these instruments work. DSA 10 discovered FRB 190523, which I think remains one of the most energetic FRBs known. It's localized to a galaxy of redshift of 0.66. This movie here in the center shows the pulse in the dirty images. Not much more to say about this first, rather far away, rather energetic. Some interesting work to be done in understanding the cyclone through which it passes, because there just happens to be a relatively bright quasar sitting right here. STARE2, of course, co-discovered the galactic FRB source, SGM 1935 to 2054, beginning to really fill in this parameter space of luminosity and pulse duration, identifying sort of intervening systems between this cloud of FRBs that exgalactic distances, as well as galactic pulsars. Now, of course, other objects also fill in this space. But also particularly interesting was the coincidence of the FRB-like emission with a hard X-ray burst, providing insight into the emission mechanism. So FRB localizations, accurate FRB localizations, are an incredibly rich vein of science. So I just want to highlight here some of the amazing work done by the LBI localizations of FRBs to show just the extreme lengths to which this can be pushed. So these images of course show three examples of VLBI localized FRBs, and I mean the accuracy is truly incredible when you consider the kind of objects with which these can be associated. Of course, FRB 121102, 1809-16 and 2001-20 I also chose these because these have quite disparate host environments, leading to a range of potential progenitor models. Of course, 121102 originated within a star-forming dwarf galaxy host. There's a co-persistent radio source. 80916 is a rather unremarkable host environment, potentially somewhat older than that of 12102. And finally, 2020 is much older than either of the others, being associated with the globular cluster of M81. I think the more we see, especially with these accurate localizations of repeaters, the more interesting but complicated the picture of their origins seems to appear. By the same token, as we begin to study more and more FRB sightlines, we begin to get more and more insights into the complex and structured and rather puzzling nature of baryons around and in between galaxies. We, of course, know that a good fraction of matter, especially in the low redshift universe, is unobserved in current censuses through either emission or absorption studies. And of course, FRBs are a great way to probe the entire baryon content, because even though the baryons are hot and almost fully ionized, FRB dispersion measures trace them in their entirety. And of course, the trick is to try and associate these baryons potentially with structure or not within the local universe. And Liam's talk next will go much more into this science case. So arc-second scale particle universe localizations are really, I think, one of the key avenues forward in addressing both progenitor science as well as what we can learn about propagation of FRBs along extragalactic sightlines. So arc-second scale localizations, of course, can reveal extreme compact object progenitor systems, as well as their evolutionary histories, what happens to them in the future, and so on. They also allow us to establish means of generating these extreme radio brightnesses, and potentially allow us to identify faint multi-wavelength counterparts if they exist. This game becomes a lot easier if you have a very accurate radio position. FRBs are very common, and so one needs to have accurate positions in order to make high confidence associations. By the same token, propagation along extragalactic sightlines requires localizations in order to, at the very least, to identify the redshifts of FRB sources to know exactly how far through extragalactic space these bursts have traveled. By then identifying systems along their sightlines, we may get some insight into the contents of various components of extragalactic baryons along the sightlines. Of course, plasma and gravitational lensing in various environments is something one can get insight into, as well as the magnetization of extragalactic plasma. So, in the literature, telescopes besides the DSA 110, which I'll introduce in a second, have published 21 arc-second scale localizations to date, and I will show how the DSA 110 is adding to this sample. So the DSA 110 is it's a radio telescope that we're in the latter stages of constructing at the Owens Valley Radio Observatory, and it will consist, when complete, of 110 4.65 meter divisions. The idea is that we have 95 antennas in this T-shaped core, as well as 15 outrigger antennas. The idea is that we can both discover FRBs with the core being coherently added, and then store data for the full array to interferometrically localize those FRBs. So the DSA 110 was designed to localize more than 100 FRBs per year to better than a few arc seconds. This 3 arc seconds, I'll emphasize, is the 4.5 max of a localization region. So you can think of it as plus or minus 1.5. the funding was originated in 2018, and we're now at the stage where we're operating with 63 antennas while completing the north arm of the T. So we were slowed by various things along the way, COVID being one of them. But as you can see from these photos, various activities have been ongoing over the last few years. We assembled these dishes on site, designed, built, and installed mounts and elevation-only drives, spliced several hundred, I believe nearly 1,000 fibers, built a road and trenched and laid out fiber power for the outriggers. Our digital backend is fully in place. We had some really great help along the way as well. And we anticipate full operations and near real-time data releases following the publication of the instrument paper this spring. So the DSA 110 had certain requirements which we believe we've met with certain technical innovations. We needed a wide field of view of about 10 squared degrees, high time resolution, excellent angular resolution, as well as absolute astrometric calibration, and finally a high observing duty cycle. What allows us to deliver these requirements are we put a lot of effort into good antenna and receiver design, and really tried to beat down systematics like pointing in order to get rid of as many sort of unknowns as possible from the system. So for example, despite the beam being 3.5 degrees across, we insisted on pointing being better than 0.1 degrees in order to maintain uniform sensitivity across that beam in a coherent sum. Our receivers are ambient temperature that deliver a 25 Kelvin total system temperature on sky, as well as a 10-year lifetime in practice per receiver. The 25 Kelvin, the contribution from the LNA itself is about 8 Kelvin. It varies depending on weather. We get some rather extreme temperature swings, and we can get a couple of tenths of % variation in the LNA temperature with the weather. The dominant contribution to the system temperature is spillover. The digital backend is the sort of classic FX architecture. We do full cross correlation and automatically calibrate instrumental gains. Also form 256 coherent beams with the core and deliver real-time FRB detection as well as data storage. So this is what part of the array looks like. You can see several antennas within part of the core. At the moment, this is the a section of our east-west arm. The north-south arm is still being built out, and rather invisible in this image are 5 of the outrigger antennas as well, sort of spanning the boundary of the Owens Valley site. So the system, it's taken us some really amazing work by the team to go from detection to reliable localizations. And this is roughly what it looks like. We discover FRBs and convert them rapidly in voltage data. This is a particularly bright FRB. We still name all the FRBs, and we still are able to refer to them by names. This one we call Wilhelm because it's particularly bright. We then are able to derive bandpass calibration as well as in-field gain calibration against NVSS Sky model using visibility data stored around each burst. This is an example image of about 10 minutes of data around one of our bursts. We then apply a fine astrometric correction using VLBI calibrators observed within sort of plus minus 2 hours of each FRB. And this allows us to correct the NVSS frame in a particular location to the ICRS frame. We then are able to image and fit the position of an FRB using an optimal DM and width, and you can sort of see here, this is a PSF for Wilhelm, as it turns out. This is a dirty image, clean image. And then finally, we derive our final astrometric accuracy from the sort of quadrature sum of the fit precision, as well as the accuracy in modeling the offsets of the LBI calibrators. And so basically, it's how well we can localize this, plus what is the scatter in these red crosses as well. And so in 2022, we had 30 FRB discoveries and localizations. These are the positions of all 30 ordered by their extragalactic DNs. It is reassuring that, at least to start with, that in the top row tends to have bigger galaxies than the bottom row, for example. In some cases, things are a bit weird. Liam will tell you about a couple of the weird ones, as will I in a minute. There are some cases, actually I'm trying to find one which is particularly unfortunate. I think it's this one here, where that is not a galaxy, that is a star that happens to sit on top of the host galaxy, which is a really unfortunate occurrence. But there's some really fun things in here that the team is only just beginning to work through. And so I'm going to tell you a bit about some of the results that are coming up. This is an incomplete list. We put a paper in the archive on the localization of the intensely active repeater 220912A to a galaxy at redshift of 0.077. It was a remarkably uninteresting host, and I leave it at that. We were able to place a constraint on baryons in the Milky Way halo from a particularly nearby FRB in a galaxy at 50 megaparsec, and this is the host, that's localization, and we were able to combine this measurement with observations of pulsars in M53, which is a globular cluster rather far off the plane, about 18 kiloparsec off the plane, as well as magellanic clouds, to constrain the baryon mass of the Milky Way halo, and the usual sort of models for the baryon content of the halo. We're able to show, for example, that the halo certainly does not meet the baryon budget, that is sort of cosmic average. So papers to come out. We have two FRBs that originate in massive galaxy clusters, including one of these from an early type galaxy. This is work led by graduate student Kriti Sharma. You can see here the star formation history of this galaxy is dominated by very large look-back times. This galaxy sits way down here in this parameter space of stellar mass versus star formation rate. And in particular, I really like the comparison between the specific star formation rate of this object, 220509, and the distribution of specific star formation rates for various astronomical transits. Really, the only one that is sort of allowed in this comparison anyway is the short GRB population, which is certainly a case of correlation that shouldn't necessarily be interpreted as causation, but it's just a striking sort of departure from at least many of the other FRB hosts. Liam will talk next about the implications for the intercluster medium. Casey Law was leading a paper on sort of a gold sample of host galaxies from our observations, and really the main result that's emerging there is an unexpectedly quiescent host population. I'm particularly excited by work on polarization with these FRBs. We're finding near ubiquitous high polarization fractions among FRBs, as well as rather rich magnetoionic environments, in that the inferred magnetic fields in the hosts of these FRBs, at least using the rough estimates of DM host, are typically larger than those that at least normal Milky Way pulsars. But honestly, I just think that staring at the polarization data is truly amazing. This is Stokes' IQUV profiles for one of these bursts, and I just like staring at this. And a better way to stare at it is in the Poincare sphere. This is all work led by graduate student Miles Sherman. And just the richness of these data are I think, amazing and really require careful thought and interpretation. I want to spend the rest of my time on new directions. So one of the new directions I will talk about is the DSA 2000 radio survey camera. This is a project underway, currently funded by Schmidt Futures, the NSF, Caltech, and Nanograv. And this is a project to build a radio counterpart to the large survey instruments of the 2020s. It is a strategic priority of the Astro 2020 Cable Survey here in the US. The idea is to build an array of 2,000. Thank you. The idea is to build an array of 2,000 5-meter dishes that are fully steerable and configured in a 19 by 15 kilometer site in Nevada, operating in a 0.7 to 2 gigahertz band. The array will be highly optimized for both imaging surveys as well as pulsar timing experiments. The idea being that it spends most of its time doing imaging, some EMGW follow-up, and spending about 25% of time on pulsar timing array science. The DSA 2000 is really driven by the need for extremely high survey speed while matching the sensitivity of some of the most sensitive instruments currently operational. So we expect to have a sensitivity comparable, for example, to FAST, but with survey speed that is something like 6 times that planned for SKA-1 mid. The idea is to be able to simultaneously do continuum as well as spectral line and polarization imaging, time pulsars, and do a fast transient and pulsar search. Key science themes, of course, include multivesicular astronomy, both with pulsar timing arrays as well as sort of follow-up of ground-based gravitational wave detector events, studying star-forming galaxies and AGN throughout cosmic history, as well as probing the dynamic radio sky. And Liam will talk next about FRB science with DSA 2000. I'd like to tell you in the final minute or two about TRACK, the transient radio camera. So we fully agree with the BURST team that aperture arrays are a very compelling future for this field, and indeed several fields of radio astronomy. And so here at Caltech, we've proposed TRACK, which is a complement to BURST that's focused on discovery. We intend a single station, the idea being to really probe the space of rare transient sources, of course nearby and rarely repeating FRBs, prompt neutron star merger counterparts, FRB-like emission from galactic magnetars, and extrasolar type 3 bursts. The idea is that we want to build a single station of a dense aperture array of 480 dual-pole Vivaldi elements in a pseudo-random configuration, including in polarization, operating in the 350-450 megahertz band, with 700 coherent beams that tile a 7400 square degree field of view. The idea then is just conduct a transient search in each beam on timescales of somewhat under a millisecond to somewhat over a second. TRACK is a relatively focused experiment. Again, just one station, and then everything brought back over coax to RF SOC boards, and then I just think it's truly amazing that we can get all the inputs with just 5 of these boards. We're intending a rather novel stacking of the RF signals in frequency in order to fully make use of these ADCs. And then operate just 5 radio camera servers to search these beams. In terms of FRB science, we really hope to be sort of a leader in FRB detection, at least in the relatively nearby universe. Exactly how far out this is the case depends on the FRB luminosity function. But I'd like to leave it at that. Instruments built through this program are delivering results on both the source of FRBs and the medium through which they propagate. DSA 110 is delivering these arc-second scale localization of FRBs at a world-leading rate. And please look out for papers coming out over the coming months and hopefully onwards. And the new directions we're exploring are the DSA 2000 as well as track. And happy to take questions. Thank you very much.
That was exciting talk. Session is open for questions and comments. Wait.
Hi, Ravi. Thank you very much, Wei Li here. Obviously, it's always exciting to hear the very rapid progress, very impressive. The track, just curious, so is that something which is an idea or something under construction, or what's the current thought for that?
It's an idea. It's something for which we have a concept, as in we seem to have a confluence of antenna engineers, receiver engineers, and digital engineers at the moment that all seem to have good concepts of different aspects of the system, and so it's proposed. And so if funding comes through, we expect to start later this year.
And the cost is driven by the RF SoC boards still, even when you stack it like that? I would have thought it gets pretty cheap.
Yeah, it is pretty cheap. That's sort of a funny thing. It's hard for me to pinpoint one thing that drives the cost. Everything's about the same, I'd say. So it's about, for example, the cost of the servers is about the same as the cost of the RF SoC boards. It's about the same as the cost of the electronics. It's about the same as the cost of the antennas. Yeah.
Okay, thank you.
Thank you very much for the nice talk. So what is the fraction of the spiral galaxies and elliptical galaxies in the population of the detected sources?
So, to be completely honest, I would say that we've analysed about half these galaxies in detail. And in that half, I would say that there is just one that we're certain is elliptical. There are others with somewhat low specific star formation rates, but I wouldn't call them elliptical. But yes, I would say there's just the one that is elliptical.
Thank you very much.
Okay, let's go to online questions.
Yes, one question from Susumu Inoyo.
Yeah, thank you for the very exciting results. So also about the those galaxies. So you showed the plot, the number versus specific star formation rate, and I was wondering. So there's the one associated with the globular cluster. Where would that fall on this plot?
So for that one in particular, we've just used M81's specific star formation rate.
Okay. So I guess for the globular cluster itself is, yeah, okay. I guess it's difficult to derive a star formation just for the globular cluster. Okay.
Yeah, it would be very low, of course, but yeah, it's an interesting question as to whether we choose that as the host, given that we may not necessarily be able to associate others at larger distances with globular clusters. But yeah, I mean, we're exploring different ways of sort of slicing this parameter space. But,
Yeah, thank you. Thank you very much.
Okay, quick, please, quick.
Very much for nice talk. I have a very quick question. How do you compare the dispersion measure distributions of DSA FRBs with chime FRBs, which is more distant?
Great question. So, I'm sorry, I don't have a plot that shows that. But if I'm sort of trying to put the plot in my mind's eye that I've seen, it's comparable. Like, our DM distributions are quite similar.
I see.
As you can see, we end up with a maximum extragalactic DM of just under 1400. And our minimum is negative 22 in this particular way of looking at it.
I see. Thank you very much. Thank you very much.
Okay, thank you for
Thanks.
the discussions. Time is up, so let's thank Vikram again.